2011 E&M number 1. Problem number 1 starts out with a non-conducting, but it's a shell and uniform surface charge density. So if we have a spherical shell, well, vaguely spherical shell, and all the charge is uniformly spread out on the outside, we can use the symmetry demanded by Gauss's law to make a spherical shell or imaginary surface for part A to analyze the electric field inside this shell. Now, this only works if there's symmetry. So our Q enclosed inside this imaginary surface of radius r is going to be 0, and it needs to be spherical also because the charge has a spherical symmetry. So surface area of sphere. So then therefore the electric field is going to be 0 over epsilon naught 1 over 4 pi r squared, also known as 0 altogether. For part B, now let's rearrange these charges. I wonder if I could do that. Nope, they're not going to let me just select one of them. For part B, if I rearrange those charges so that they are not spherical, so that they're not symmetric, so we'll go like, whoops, go like that, and suppose we put all the charges on this one side. How many did I have? 10-ish, 9-ish? Just have a whole bunch over here on the one side. So now even if we put our Gaussian surface inside like that and we have no enclosed charge, what we have is, instead of all of these charges producing electric fields radially inward and then they all cancel each other out by vector addition, that canceling each other out is not going to happen. Now all those arrows point vaguely in the same direction, and maybe the up and the downs cancel, but the way I've drawn it here, the left and the rights won't cancel. So if it's not uniform, the electric field is not 0 inside the shell. So we can say the net effect doesn't cancel. Therefore, the electric field is not 0. All right, for part C. Now we're going to shrink that charge down so it's essentially a point charge and put it on one vertex of a cube at point A. So where is the electric flux equal to 0? Now the electric flux, you come back to part A here, the electric flux is when the electric field through an area. That's going to be the electric flux. So if we take this charge and we draw an arrow on A, B, C, D from A to C, that's going along the surface. It doesn't cross over the surface. So A, B, C, D, that's not 0. How about if we draw a representative arrow from A to E? That is going along the surface, not across the surface. Keep in mind that these two vectors, the electric field has to cut through the area. It's not cutting through that area. So A, D, E, H, that's another one. And then the last guy is A, B, G, H. If we draw a representative arrow from A to G, it's not cutting through that area. it's going along the surface of that area. So E field lines must cross through an area. Those three surfaces, the E field is parallel to the surface. It doesn't actually cross the plane of the surface. All right, at which corner does the electric field have the least magnitude? Well, keep in mind that we still have a sphere here, and the center is at A. Well, what that means is that A is inside the sphere. Also, it's conducting. So EA equals 0. All of the other labeled vertices have a non-zero electric field at them. A is a special case, and this sentence is very important for answering part D. All right, E. Well, for part E, again, if we go back here to my original drawing, if this is our little tiny sphere and the center of the sphere is point A, what we would do is draw our Gaussian surface around that point, say, hey, there's no enclosed charge, so Q enclosed at point A is 0, so therefore the electric field at point A is 0. Given that 1/8 of the sphere at point A is inside the surface, okay, so if we take a look at our cube, and one chunk of that is inside there, what's going to be the flux? Well, for part F, Q enclosed is going to be Q over 8. And if we go back again to part A, Gauss's law, Q enclosed over epsilon naught is equal to EdA is equal to the flux. So let's just skip over to the flux. So if we divide by epsilon naught, divide by epsilon naught, that is going to tell us the flux through all the rest of these surfaces. But then you have to keep in mind that out of the 6 surfaces, 3 of them have 0 flux. That means the other 3 each get 1/3 of the flux. So cube equals 6 faces minus 3 faces with flux equal to 0. So 3 faces get all the flux. So what we want is flux through that one surface of CDEF equals 1/3 of the total is going to be Q over 24 epsilon naught. That looks like that's all of number 1. So I'll clear out and we'll look at number 2.